All right, Algebra 2, 6.4 gets us into a discussion now of rational exponents. And before we get too far into it, let's just take a second and remember what we're doing here in Chapter 6. It's all about rational expressions, and we're eventually going to be solving and graphing rational equations and functions. When you hear that word rational, just remember that rational is a mathematician's word that basically means a fraction. There are rules there. It's got to be a fraction of, I think, integers on top and bottom, but rational means fraction. And if you guys can remember that, you'll be in pretty good shape. And so let's take a look here, guys, at what it is we're going to be doing within this section right here. We are going to be taking a look at fractional exponents now. So the first box that we have here is what to do with a, which would be called the base of your exponent, raised to a power that's 1 over some other number, n. And the whole point of 6.4 is that a fractional exponent can be translated into a radical. We just need to understand what goes where. The base of the exponent, a, becomes the radicand, the number you're taking the root of. The denominator of that fractional exponent, which in this case I've written as n, becomes the index of your radical. And that's really it. We don't do anything with the 1 there in the numerator of the fraction, but I'll explain in just a second where that comes from. So right underneath that, just if you wanted, we could write a couple of examples. If I gave you something like a to the 1/2 power, we'd rewrite that with a radical. A would still be the base, but the index would be 2. But we never write an index of 2, that one is just assumed. If I gave you something like a to the 1/3 power, now that becomes a radical with a for the radicand, and now the index is 3, and so on and so forth. However, the more universally applicable version of this expression formula here is over here on the right, a to the m over n. Well, this one looks really similar to the one that we just started with, and it has a lot in common. We still are going to rewrite this with a radical. The base of the exponent a is still going to be the radicand, and the denominator of the fraction, which you'll notice is still n, is still going to be your index, and that's going to go right there. The only thing that's different now is the presence of this m, the numerator of that fractional exponent. And so what that becomes, everybody, is an exponent that's acting right there on the radicand, a. And this is a weird thing in math. This doesn't happen that often. You actually have two different choices here, two different options for where you can put that m. You can put it where I wrote it right there, but that implies that the first thing you're going to do here is take this value here, a, and raise it to the m power, which, boy, could be a really big number really, really fast, and then take the nth root of that large number. But the other option you have here is to write it just a little bit differently. In parentheses, we can start off by taking the nth root of a first, close off your parentheses, and then apply the exponent after that. And guys, it's this version right here that I really recommend that you guys try to practice. And the reason being, because the first thing you're going to do here is take the nth root of a, which is going to take a number that might be pretty big and knock it down and make it smaller first, and then you'll worry about taking that small number to the m power. So I'm not going to do any examples of that because that's what we're working on here really for the rest of this section right here. So let's start off with something like this, 625 to the 1/4. And really your directions right here, which I should have written out, could be written as simplify. You might also just see the word evaluate right here. What is 625 to the 1/4 power? Well, really all we're doing here in 6.4, guys, is translating back and forth between rational or fractional exponents like we have right here and radicals, which you guys are more familiar with because we've spent the first 3 sections here in Chapter 6 dealing with radicals. So the base of the exponent, 625, is your radicand, and the denominator of the exponent, this 4, is going to become your index. Now, I said I would come back to this later, and I forgot to. The numerator of that fractional exponent, 1, is an exponent. And if you wanted, you could put it right here on the 625, or you could put it out here and worry about it after you evaluate that fourth root. But it doesn't matter because anything to the first power is just equal to that number itself. So with a 1, we don't bother to write it as an exponent anywhere. And at this point, guys, this is really the takeaway from this problem. 625 to the 1/4 power can be translated into the fourth root of 625. And at this point, you guys would probably grab your table of all your perfect squares, cubes, fourths, and whatnot. And what you're going to find on that table, give me a second here, guys. If I was thinking, I would have had this ready to go right here. It's the power table. Where did it go? Where did it go? That's not it. That's not it. It's here somewhere. Shoot, I think I passed it. Pause for a second here. Okay, pausing didn't help. There it is, Algebra 2 power table. That's what I was looking for. And the hope would be that 625 is going to show up in your column here of perfect fourths. And what do we got here, guys? Yeah, sure enough, there it is, guys. 625 is found in this cell right over here. And when I run that over to the left, yeah, I see the fourth root of 625 is 5. Okay, very convenient. So that's it, everybody. 625 to the 1/4 power is 5. Now, do we know that that answer is right? Well, there's a lot of different ways we could check it, but the way most of you guys would probably choose to do it would be to grab your calculator and just take 625 to the 1 divided by 4 power. You can use a fraction there, or just use the division key like I did, and sure enough, we got 5. But I want to remind everybody, just about all of our tests and quizzes that we take in here have a calculator and a non-calculator section. This is a problem that would almost definitely show up on the non-calculator section of that test because there's really no skill to just typing it in there. We want to know if you guys are able to convert it into a radical and then evaluate that. So this is a non-calculator question, but you will be able to use your power table on a problem like this. Let's look at example B right here, 973 to the 1/5. So the first thing we're going to do, just like the last problem, is change this into a radical. 973 will be the radicand, and the denominator of the fraction, 5, becomes your index. And again, when your numerator is 1, you don't really have to worry about that at all. So what are we supposed to do with the fifth root of 973? Well, we would take a look at our column of perfect fifths over here on the right, and we would hope that we see 973. We don't. Okay, so 973 itself is not a perfect fifth. Then what we would do is start looking at perfect fifths that are less than 973, and really less than half of them. Although this is going to be pretty quick here, guys. Half of 973 is probably what? Somewhere in the neighborhood of 486.5, if I did that right in my head. Doesn't really matter. There's really only two numbers that could work here. 32 and 243. And I'm pretty sure, if I remember this problem right, neither one of them is going to work out very well. 973 divided by 243? Nope, that one didn't come out evenly. Your calculator would have given you this. And then how about 973 divided by, the only other perfect fifth in that table was 32, and when I try that, nope, that one ended up being a decimal as well. What that means, everybody, is that this is kind of a dead-end problem. All you can really do here is convert that thing into a radical, but it doesn't simplify at all. So depending on what the directions would say, maybe you would just leave it here the way it's written. Maybe you would say cannot be simplified. And if we wanted it as a decimal, if I did the old approximately equals to, I guess at that point on your calculator, you guys would hit math and 5. I think for me, I got to hit this thing right here and just go ahead and say, all right, what is the fifth root of 973? And I think we're going to have to then, yep, there it is, 3.96 if we were going to round that. But again, the directions are really the important thing right there, guys, and you're going to have to see what they tell you to do. All right, not a very interesting problem. Now let's take a look at this one. -8, and you'll notice that's in parentheses, raised to the 2/3 power. So just like everything here, we convert it into a radical. -8 is your radicand. The denominator of that fractional exponent is your index. So that's a 3 here. And now you guys have a choice for where you put the 2. You could square the -8 first and then take the cube root of that. But I think that's probably the wrong way to go with this one, guys. What I would do is put parentheses around all of that and then square the result. So let's do what's inside the parentheses first. The cube root of -8, well, luckily, 8 is a perfect cube. Its cube root is 2. That means that this cube root is going to be -2. And if you think about that, -2 times -2 is +4, times another -2 is -8. And then we'll square that whole result there, and -2 squared. Notice I still put parentheses around that. -2 times itself, -2 times -2 is +4. So this again is a problem that is likely to show up on the non-calculator portion of your test here on Chapter 6. Let's do another one. 25 to the 5 halves. Now, I want to point something out right here. Fractional exponents are weird, but one thing is kind of true. This problem, I tell you what, let's ignore the negative for a minute, and let's just focus on the fact that 8 to the 2/3 power, it would still end up equaling 4. Let me write something dumb right above this here, guys. 8 to the 1st power, let's think about that, is going to equal, well, that's just 8 by itself. And 8 to the 2nd power, 8 squared, is 64. What I want you guys to notice is that the bigger your exponent is, the bigger your product is as well. 2 is bigger than 1, and 64 is bigger than 8. Okay, and 8 cubed is going to be even larger than that 64. Let me think. That's 2 to the 9th, which I believe is 512. This exponent, though, in the original problem, 2/3, was smaller than 1. So if an exponent of 1 gets you a product of 8, I think it makes some sense that an exponent of 2/3 is going to get you something smaller than 8. And by the way, we haven't talked about this that much that chapter, but any number raised to the 0 power is equal to 1. Well, sure enough, this 2/3 right here is in between 1 and 0. And so its product is in between 8 and 1. So hopefully that makes a little bit of sense. Now, why do I bring that up? Because right now, we're being asked to take 25 to the 5 halves power. So real quick down on the bottom, let's just play around with this a little bit. 25 to the 0, anything to the 0 power is 1. 25 to the 1st power, well, that's just the number itself, which is 25. 25 squared, oh boy, that's a big one, is 625. Trust me, kids, I'm a professional. And 25 cubed, okay, shoot, now I'm out of luck and I don't think I know that one. So let's do it together here. 25 to the 3rd power, wow, big number, 15,625. Let me write that down. 15,625. Now, why do I bring all that up? This fractional exponent right here, 5 halves, is 2.5. 2.5. So the value of 25 to the 5 halves, or 2.5 power, has to be somewhere between the value of 25 cubed, which was this number, and 25 squared, which is this number. So I'm expecting this result now to slot somewhere in between these two numbers here and here. So I'm expecting an answer bigger than 625, but smaller than 15,625. Okay, that's just kind of a way I want you guys thinking about this logically here, but let's do the problem straight up here. We're going to convert our fractional exponent into a radical. 25 is our radicand. 2 is our index, but of course you never have to write an index of 2. There you go. And that 5 becomes an exponent. Now you could put the 5 right here, but now you need your calculator to evaluate 25 to the 5th power, which is really, really big. So I think it's a much smarter move to put that 5 out here and then actually do the square root of 25 first. Either way will work, but that other way just, gives you some really big, ugly numbers, and this tends to make it a little bit easier. So what do we have here, guys? The square root of 25, of course, is 5. And we're going to take that to the fifth power. And let me think about that, guys. 25, 125, 625, and that times 5, I believe, is going to be 3,125. But I guess I better check that. I don't want something wrong in our notes here. 5 to the fifth power. Yeah, okay, I had that right. 3,125, and that's going to be our answer. And sure enough, I was looking for something bigger than 625, but smaller than 15,625. And so I at least got a number that's realistic in that regard. So maybe just something to think about as you guys are going through these problems. Because I'll tell you, one of the really common mistakes people are going to make is they'll write this as a radical, but they'll goof up the order. They'll put a 25 right here, but they'll put a 5 for the index and then a 2 for the exponent. Now, if you were to do that, the fifth root of 25 comes out to be an ugly irrational decimal, and then you'd square it, but you're going to get a number smaller than 25. But we just thought about it for a minute. Since this exponent is bigger than 1, the answer we came up with has to be bigger than 25, and it was by quite a margin. All right, guys, so that's just kind of a quick little recap, or an introduction, really, to what it is that we do with fractional exponents. So we're going to start using that to simplify some complicated expressions, but there's a couple rules here that I want to make sure everybody knows, and I might actually add a few to what I have right here. The first one is what happens when you take a monomial base, AB, they're being multiplied, so that's a monomial, but with several factors being taken to a power. And what you guys can kind of see here is that that exponent of m applies to every factor of the monomial base, A and B. So I really hate to say this because it's technically not accurate, but you guys would probably make this conclusion on your own if I didn't say it. What we're really doing here, guys, a lot of people see it as, is distributing that exponent backwards to get A to the m, B to the m as well. That is not the distributive property. The distributive property is what happens when you take a monomial multiplied by a polynomial. There's got to be a plus sign for that to work out. So this is the distributive property, but a lot of people view this as a distributive property for exponents. As long as you guys know it's not really the distributive property, I think we'd be okay. The second property, this one right over here, deals with the division of monomials that have the same base. All right, we have a to the m power divided by a to the n power, and that becomes simply a to the m minus n. We take the numerator exponent minus the denominator exponent and write our answer that way. While I'm going through the property here for division of monomials, I don't know why I didn't have this written down already, let's talk about the property for how to find the product of two monomials. If you're multiplying these two things together, you're going to keep the base the same, but now you're going to add those exponents together and get m plus n. So you'll notice this expression right here and this expression right here are almost identical. It's just that when you are dividing, that's when we subtract exponents. Top minus bottom, m minus n. But here in number 3, when you're multiplying, that is when we add exponents together. And I think a fourth property we probably should talk about would be something like this. If you have a monomial with an exponent like a to the m in parentheses, and then that is being taken to a new power, n, this is the case that we call a power of a power. And in a case like this, guys, this is when you multiply your two exponents together. This is the same base, a, but then we take m times n, which is going to be mn. All right, so these are probably the big 4 ideas, not really in a great order. I probably should have started with this one right here. I've called that one number 1, this one number 2, maybe, yeah, probably this guy 3 and this guy 4 in terms of how often they come up. But anyway, the order here doesn't matter. Let's keep all that in mind, and let's try to simplify this expression right here. Now, this looks similar to some simplification problems that we saw, I want to say, in section 6.2, a monomial on the top divided by another monomial on the bottom. But in 6.2, we said you could only simplify an expression like this if the indices were the same. Well, I've got a fourth root on top and an eighth root on bottom. So in 6.2, we would have said, nope, can't do anything here, cannot be simplified, and just moved on. But now we know some new tricks here in 6.4 that we didn't know before. So let me show you what we're going to do right here, guys. We are going to convert. We're going to do the opposite of what we were doing with problems earlier here in this section. On these problems, I gave you a fractional exponent and wanted you to convert that into a radical. Now we're going to go the other direction. We're going to convert radicals back into fractional exponents. So the radicand here is x. That becomes the base. For the fractional exponent right now, the index, which in this case is 4, becomes the denominator, and the exponent here, 3, becomes the numerator. So guys, that's x to the 3/4 power. That is not x times 3 over 4. That's something different here, not what we're doing. That's x to the 3/4 power. Down on the bottom, the radicand is still x, and let's take a look at the fractional exponent. The index is 8, that goes on the bottom. The exponent is 2, that goes in the numerator. But I kind of hope that you guys just saw what I saw. Never in your life should you write out the fraction 2 over 8. You should recognize, hopefully right away, that 2 and 8 can be simplified. They're both divisible by 2, and it becomes x to the 1/4. So all we've done now is use the skill from earlier in this chapter to convert radicals into fractional exponents. But now, let's take a look at property number 2 here. This one deals with the division of monomials. So you can take a to the m power divided by a to the n power and just make it a to the top minus bottom exponent. So this becomes just an x, and the exponent from the top is 3/4. Minus the exponent from the denominator, which is 1/4. So that is going to become x to the 3/4 minus 1/4 is 2/4, and 2/4 then, of course, becomes a 1/2. So you could write your answer here as x to the 1/2, or since the original problem was written, take a look in the blue there, using radicals, you could write this one with a radical as well. X is your radicand, the denominator of your fractional exponent 2 is your index, but we never need to write a 2 there, and the 1 is your exponent, but we never need to write a 1 for a power either. So either form there, guys, x to the 1/2 or the square root of x, either one of those would be okay. So that's how we would handle a problem like A. Now, B, that I'm going to do with you here, is a serious pain in the neck right here, and maybe this was too tough of a problem to give you guys, but we're going to run through it anyway. We've got a bunch going on in parentheses, negative 8x times the square root of xy, all of which is taken to the 2/3. Now, what we're kind of dealing with here, guys, are apples and oranges. Right here, we have a radical, and right here, we have a fractional exponent. We want to get things one way or the other, but we really don't need them, or we don't want them as both. So I'm going to convert this square root here inside the parentheses into a fractional exponent. So I'm going to keep the negative 8x out there in front. And in parentheses, parentheses within parentheses, here's the xy, and a square root, remember guys, your index is 2, becomes a 1/2 power right there. So that takes care of the square root of xy, and all of that is getting taken to the 2/3 power. Now, just like always, we try to clean up inside parentheses first, so that's where we're going to focus. The negative 8 and the x are going to stay put for now, and right here, guys, we have a 2-factor monomial base, xy, being raised to a power. So that 1/2 is going to apply to both the x, so there's an x to the 1/2, and to the y to the 1/2, and all of that is going again to the 2/3 power. And there's a little bit more we can do inside the monomial base right here. Negative 8 times, what do we have here, guys? X, which is actually x to the 1st power, multiplied by x to the 1/2. So now I would talk about property number 3 here. When you're multiplying monomials, add their exponents together. So 1 and 1/2 is going to be 1.5, or 3/2 is probably the better way to do that. X to the 3/2 and then y to the 1/2. And all of that is going to the 2/3 power. Now, there is nothing else we can do inside that base, everybody, inside the parentheses. Negative 8, x to the 3 halves, y to the 1 half. It's all you can do. So now we have a 3-factor monomial base being taken to a power. This is where you guys are going to tell me we backwards distribute that exponent. So what's going on here, guys? Negative 8 is going to get taken to the 2/3 power times, now this is interesting, x gets taken to, we have a power of a power. This is when we multiply our exponents together. And 3 halves times 2/3, let me write that over here, 3 halves times 2/3. Well, if you remember what we did in chapter 8, guys, when you're multiplying two fractions, identical factors on the top and the bottom cancel each other out. This 3 cancels with that 3. This 2 cancels with that 2. And when everything is gone, you're left with a 1. So this is really x to the 1st power, and we don't bother writing the 1. And then it's going to be y to the, well, let's try this. Right here, we had a y to the 1/2 power multiplied by this 2/3 right here. So a 2 on the bottom and a 2 on the top cancel, but that's it. That leaves me with a 1/3. So then it's going to be y to the 1/3 power, and that's where we are at this point. Now, we're not done with this problem yet, but we are definitely getting closer here. So let me move some things around a little bit. Okay, this will work. All right, we're going to translate this fractional exponent into a radical. Negative 8 is the radicand, the denominator, 3 is the index, and then 2 is the exponent. Can't do anything with that x, so that just tags along, and I think I'll rewrite the y to the 1/3 as the cube root of y. And then one step here, guys, and I think we're done if we do two things at once. The cube root of negative 8, we've already talked about in this video, is negative 2. Negative 2 squared is going to get you a positive 4. There's the x. And then the cube root of y is what goes at the end. There is nothing else in the world we can do to simplify that answer, so that's what we came up with here for example B. That's a tough problem. There was a lot going on in that one, and it was kind of a pain in the neck, but we got it eventually. All right, guys, that's as much as I wanted to do with you from section 6.4. Hopefully that gives you a good shove in the right direction, so start that homework and let us know how it goes. Good luck, everybody.